Hello, class. Today we're going to begin a new lesson. We're going to look at section 9.2 and look at how to graph polar equations. So we just came off of lesson 9.1 where we were converting rectangular equations into polar equations. So now that we know how to do that, you're going to continue using that skill. And then after you've converted it, we're going to see what that looks like on a graph. Now, the first thing you might be noticing is this graph paper doesn't look the same as usual. And that is true because this is a polar grid, and this is probably the first time you will have experienced graphing on a polar grid. And I put some blank graph paper in the Google Classroom. One of them I set as a PDF document. So hopefully maybe you have a printer at home and you can print a few pages of that to use that on your homework. If you don't, I also put I saved it as like a Microsoft Paint file that you might be able to open. So if you have like a Chromebook or a Windows computer at home, you might be able to open it and then you can draw them on there and then save them and maybe somehow upload that to your homework. And so I know you guys are really creative and you're good at figuring things out. So I really would like you to practice graphing on polar grid. So if somehow or another you can work to either print that out or to do it digitally, like in Paint or some other program, perhaps an app on your phone or something like that, I really would like you to attempt to do that. Yeah, I suppose you could draw it out by hand, but that's probably not going to be very fun and that'll get very redundant. So if you could try to find a way to actually use this polar grid, that would be great. So as we take a look at our polar grid for the first time, you'll notice it looks a lot like the unit circle. You will notice there's some extra places on the polar grid that we don't usually look at on the unit circle. We usually look at pi over 6, pi over 4, pi over 3, pi over 2, and multiples of those. But you will also see that we have multiples of pi over 12. And so that's going to help us. We may not actually use those today, but that spot on the circle will certainly help us as we look at some future polar equations to graph in this lesson. And you might be wondering, why do we need a polar grid for? Why can't I just graph the way we've always graphed? And you can graph rectangular equations on a polar graph. You can also graph polar equations on a rectangular graph. You'll just see that it's not always as compatible, and sometimes it's easier to read if I have a polar equation to put it on a polar graph. Or if I have a rectangular equation, sometimes it's just easier to look at and it's more compatible and makes more sense to be on a rectangular graph. So I think you'll kind of see that as we get started here. It'll probably take a few examples, but once we get going, I hope you'll start to see why a polar grid can be really helpful to us. Before we look at any specific polar equations, I thought I would remind you, you've actually already graphed some polar coordinates before. We just didn't put them on a polar grid. You might remember the beginning of the lesson 9.1. You were given some coordinates that look kind of like this. Remember, the r value comes first, then the theta value. And I had asked you to graph them. And we said that theta was the angle, the direction that you would go in, and then r tells you how far in that direction that you go. So we already know how to graph polar coordinates. This is just the first time we'll be putting them on a polar graph. And so let me show you in real time what that looks like, and then we'll actually graph some equations. So this first one in red, it says r is 2 and theta is pi over 4. One thing I want to encourage you to do, and it might feel a little redundant and you might forget sometimes, but I think it's really important to show where your polar axis is before you start. And the reason that's important is if you can maybe visualize with me, say you're looking at this this polar graph and pretend like it's maybe like in 3D, and let's say you're in outer space and you're looking down on the Earth. And so if I said, go over pi over 4 radians, you would say, well, from where? If you're looking at, like the North Pole might be your pole, okay? That's why we call it the North Pole. It's the top of the globe or the top of that circle. But if I said from the North Pole, go pi over 4 radians, you would say, okay, well, where's my starting point? If I'm going to measure an angle, whether it's in radians or degrees, I need a like an x-axis, or what we call in this case a polar axis, as your starting point. Okay, that polar axis can technically be anywhere you want. You can put it right here if you want. You could put it here. And if I said travel pi over 4 radians, you would travel pi over 4 radians from this line or this pole or polar axis. But typically, we like to put it towards the right. And I think the reason we probably like to do that is because we're used to the x-axis going to the right in that direction. And so that feels familiar to us. And if we do that, then when we say go pi over 4 radians, we can say to do that from our polar axis that we've drawn. Now, there might be reason in the future sometimes to make the polar axis somewhere else, but that's going to be our default. And so as you do your homework today, I would always make your polar axis first and have it pointing to the right, just like your x-axis would. And if we ever have reason to change that, I'll make sure to warn you ahead of time before we do. So now that we've established that, the angle is pi over 4, so we'll go over to pi over 4. R is 2, so we just travel down 2 units and we place our point. For the next one, 4, negative pi over 3. This time the angle is negative. We'll use the same polar axis, so I'm going to go left pi over 3, which will take me to 5 pi over 3 if I were going forward. But I'm going backwards, so that'll take me here. If R is 4, I'm going to go in this direction. So 1, 2, 3, 4, and so that point goes here. And then the next one, negative 1, 5 pi over 6. So since the angle is positive, I'll go to the left counterclockwise like usual. So 5 pi over 6 is over here. And normally I would go this direction, but since R is negative, keep in mind from that lesson we did that we go backwards. So I'm going to go this direction and put that point right here. Okay, so again, this is really just review, other than now we're just putting it on a polar grid rather than, graphing by hand like we were doing a few days ago. Okay, so let's take a look at our first example, and this is how your homework's going to read. The directions are going to look this way. It says transform the polar equation into a rectangular equation, then we're going to identify and graph the equation. So when I look at this equation, it says R equals 4, so that's clearly a polar equation. And I have kind of a sneaking suspicion of what this is going to look like already before I transform it. The reason I do is because when I see this, it reminds me of an equation like this, y equals 4. And what's unique about this equation is that y is always equal to 4. And so, I have kind of an illustration down here where, do you see how no matter what x is, whether x is negative 4 or 2 or 5 or 10 or 100, y is always 4. And so what that does is it graphs a horizontal line at y equals 4. So since there's no other variable here, a lot of times polar equations have an r and a theta, but since there's only an r, that tells me that this is a graph where r is always 4. So maybe before we actually start, you could pause the video and kind of think about, well, what might that look like? What would an equation where r always has to be 4 look like? All right, do you have a guess in your head? Now, before we actually start graphing it, let's follow the directions here and kind of do what it says. It says transform this to a rectangular equation. Well, the good news is we already know how to do this. We just did this in the last lesson. So remember, the book offered 2 suggestions. You could either multiply both sides by r or square both sides. I think I like the squaring both sides recommendation here. And by doing that, we get r squared equals 16. And you might remember that r squared equals x squared plus y squared. That was something we used in the last lesson. And that still equals 16. And so hopefully now you're recognizing this as a circle. And I kind of wonder, does that agree with the answer that you just thought of? And to be more specific, this would be a circle with a center at 0, 0, and a radius of 4. Okay? So now we can maybe take this information and bring it to our polar graph and think about what does that look like. So let's take our original equation and our new equation and kind of think about, well, what does that mean? Well, I know the radius is 4. And if this were a rectangular grid, I would start at 0, 0, where our pole is kind of like our point 0, 0. So we can kind of pretend like we're starting right here. And remember, no matter what graph we're going to do, we're always going to start by showing our polar axis. Okay, that again kind of gives us reference for our angle. Now, we don't have any information about an angle, but we know that r is always 4. So let's think about, like, if this were my 0, 0 point and r was 4, what does that mean? Well, that means from that point, I'm going to go 4 units in every direction. So if I were going to go straight up, I would go 4 units and I would put a point. If I were going to go straight down, I would go 4 units down and put a point. If I were to go straight to the right, I would go 4 units to the right and put a point. Straight to the left, same thing. Or you could pick any angle. You could pick pi over 4 and go 4 units in that direction. You could pick negative pi over 6 and go 4 units in that direction. Oops, I think I need to fix one. There we go. And so what this equation is telling me is no matter which direction I go, I'm always going to go 4 units in that direction. So if I were to connect all those points, it would look something like this. It would look like a circle with the center at the pole and a radius of 4 units. So going 4 in every direction. And so if you were graphing this on your own, again, start with your polar axis, and then you'll end up with a picture of a circle. So I think we've answered all the questions here. It says transform into a rectangular equation. So we have that here. We identified that it's a circle, and we made the graph. All right, here's our next example. It says theta equals 2 pi over 3. Now this graph is kind of interesting as well, because this one has a theta, but it doesn't have an r. And so what that means is that r can be whatever value you want, and the angle will always be 2/3. So again, maybe you could pause the video for just a moment and just kind of guess what that might look like. What kind of graph would have an angle of 2 pi over 3, and it has to be that angle only, and r can be whatever it wants? You think you have it? Well, first I would draw my polar axis, and then I'm going to go to 2 pi over 3. And since r can be whatever I want it to be, that means I can put a point here if r is 1. I could put a point here, r could be 2, or r could be 3, or it could be 4, or perhaps it could be negative even. R could be -1, or -2, or -3. And so now you can kind of see what's taking shape is that I have a line. It's simply a line. It's a line that goes forever in the direction of 2 pi over 3. It also goes forever in the direction of -2 pi over 3, or sorry, negative pi over 3. And that's because r can be positive or negative. So if it's positive, it'll head this direction. If it's negative, it heads in the opposite direction. And so for my line, I could draw something that looks like this. Now you might be thinking that I went out of order, and I certainly did. So now that we've already kind of established what this graph might look like, let's see if we can justify that by transforming the equation, the polar equation, to a rectangular equation. Now this one's a little bit tricky. If you go back to our last homework assignment, I don't think we had one that was quite like this. You'll notice there's a theta and there's no r. And we had a couple suggestions. One was multiplying both sides by r. I don't think that helps us in this case, because then you just get r theta equals 2 pi over 3 r, and that's kind of weird and not helpful. If you try squaring both sides, you get theta squared, and again, that's not really familiar or helpful. And so I'm going to show you a new trick that we can use. And what we can do here is we can basically take the tangent of both sides. So you know the age-old rule, whatever I do to one side of the equation, I can do as long as I do the same thing to the other. Well, I can take the tangent of theta as long as I take the tangent of 2 pi over 3. And at first, you might be wondering, well, why are we doing this? But you'll quickly see that it becomes quite helpful because we know that tangent is the ratio of y over x. And so I can change tangent theta to y over x. And that's very helpful because y and x are the variables that I want for a rectangular equation. And then on the right side, I actually know the tangent of 2 pi over 3. If you think about your unit circle, we know the x value for negative 2 pi over 3 is negative 1/2, and the y value is root 3 over 2. So if we just take the y value, root 3 over 2, over the x value, which is times the reciprocal, negative 2 over 1, the 2's cancel, leaving me with negative root 3. And so the tangent of 2 pi over root 3 is negative root 3. And then we can multiply the x over, and you get y equals negative root 3 times x. And now we can see that this is an equation of a line. You can see your slope-intercept form, right? Looks like we have a slope of negative root 3 and a y-intercept of 0. And that is the equation of the line that we just graphed. And if you think about, like, if this were an xy coordinate, wouldn't this equation y equals negative root 3 over x look kind of like this? Like if you could pretend this is 0, 0, and something with a negative slope is going to go down from left to right. It's going to go down root 3 over 1, down root 3 over 1, down root 3 over 1. And so there you have it. You've got your equation, and we've got our graph. And we've identified the equation as a line. All right, here's our next example. R sine theta equals 3. This one, I don't think we have to do anything too fancy to turn into a polar coordinate. I don't think I need to multiply by r on both sides or square both sides because we already know r sine theta equals y. So I think I can simply just say y equals 3. And I know what y equals 3 looks like. It's a horizontal line. And so that's what I'm thinking we're going to have on our graph over here on the left. Now, this is one of those ones where, you know, how do I draw a horizontal line on a polar grid? Okay, and that's kind of what I was talking about earlier is, you know, how I was saying, you know, sometimes it makes sense to graph things on a polar grid, but sometimes it makes sense to graph something on a rectangular grid. This one makes a lot more sense to graph on a rectangular grid. Just as maybe, you know, I could convince you, if we go back a few examples, it makes a lot of sense to graph a circle on a polar grid. Okay, those are very compatible. Okay, it's easy to see this graph and how it fits on here. Whereas, you know, sometimes when we're graphing a line, you know, it's not quite as compatible, but it doesn't mean we can't do it. It's just like we could still graph a circle on a rectangular grid. We could. Maybe it looks a little nicer on a polar grid, but we could still do it, and we've done it before on rectangular grids. So just because graphing lines on rectangular grids is maybe nicer, that doesn't mean we can't do it on a polar grid. We just have to be careful about how we do it. So as always, we'll start with our polar axis going towards the right. And I think I'll start with, you know, if I know y equals 3, I know one coordinate that is really easy to put on a rectangular or polar grid is 0, 3. Okay, that's going to be straight up 3. So if I count 1, 2, 3 units, I can put a point right here. Now we have to be careful. It might be tempting to say, okay, well, my next point will be any other direction 3 units. But that's r equals 3, not y equals 3. This is saying y equals 3. And so to think about y equals 3, we have to think about this polar axis acting kind of like our x-axis. And so from this polar axis, I need to go up 3 units. And so I might have a point here, and I might have a point here, and I might have a point, say, here, or here, or here. Now you'll notice these points are just kind of floating randomly. They may not be on one of these angles. You might say, well, this looks like it's, you know, 4 units away. But again, we're not talking about r, we're talking about y. Okay, yes, this is 4 units along, like in value of r, but it's not, that's not what we're graphing. We're graphing y equals 3. So I'm going this 3 units up from my polar axis, or from what we would normally say is our x-axis. Okay, or down here, we're going up 3 units. Okay, regardless of how far away it is from the pole. Okay, so when we're done, we can kind of think about, well, what is that graph going to look like? Well, It's just going to be a horizontal line that is at y equals 3. Okay, now again, your thought might be, well, this is kind of silly. Why would I graph a horizontal line on a polar grid? Well, most of the time we don't. We would just graph it on a rectangular grid. But I just want to have you see that we could, just like we can graph a circle on a rectangular grid, even though it might look nicer on a polar grid. And so we certainly can graph a horizontal line on a polar grid if we want to. We just have to be careful about what we draw and what it looks like. Another example you could think about, I'm not going to do one in our notes today, but if I go back to the original here, what if this said r cosine theta equals 3? Maybe you could pause for a moment and imagine what that would look like. We know r cosine theta is x, and so that would be x equals 3, which is a vertical line. And so instead of going up 3 units from the polar axis, I would start at my pole and I would go right 3 units or right 3 units. If you could kind of imagine where your y-axis would be up and down, and you go 3 units over to the right from that, what would that y-axis be? And so that would give you a vertical line 3 units away. So you might see something like that in your homework. Okay, here's another example that's a little bit different. It says r equals 4 sine theta. So first, this one, to me, this one's not very obvious what it is. We're still kind of new to polar equations and polar coordinates, and so unlike maybe the r equals 2 or the theta equals pi over 4, this one is not quite as obvious. And so I think if we take the time to transform this like we did in lesson 9.1, I think it'll become clear what we need to do. So I think on this one, I kind of like the idea of multiplying both sides by r, so we can say r squared equals 4r sine theta. And from this, it becomes helpful to replace r squared with x squared plus y squared. And then we know r sine theta equals 4y. Okay, now at the moment, it may not be super obvious what this is, but I think if we kind of delve back into our algebra, or perhaps way, way back to chapter 1 earlier this year, what I'm seeing or thinking here is that y squared and that 4y need to go together. So I'm going to subtract the 4y over here. And then you might recall that we've completed the square. And I'm going to do that with the y terms. And so I've got y squared minus 4y. And if you take half of -4, that's -2, and square it, you get plus 4. And then whatever we do to this side, we have to do the same thing to this side. So we need to add a 4 over here as well. And so then what that allows us to do is we can factor the y terms, because it's now a difference of squares. It's going to be y minus 2 squared equals 4. And then this really looks a lot more familiar to me now. Like when I look at this, I see that this is a circle. So we've identified the graph like it wants us to. And more specifically, I know that it's a circle at center with a center of 0, 2 and a radius of 2. Okay, so now that I know it's a circle, I have a pretty good feeling that I can maybe graph this on my polar grid. So let's keep that in mind. Our center is going to be at 0, 2. So let's place our polar axis first. And then 0, 2, again, you can kind of pretend like your y-axis is still going straight up and down. And so if I had the point 0, 2, that would take me up here. And we said that our radius was 2. And so what that means is we just need to go in a distance of 2 units in every direction from that center. And so it'll be easy to come up with the first 2 points. Like if I go straight up to here, I can still just keep counting along here. So 2 units up, 2 units down will take me back to my pole. And then the 2 units right and left, those become a little tricky because, I don't want to just, I'm going straight to the right. I'm not following this circle. I'm going like kind of pretending like there's a horizontal line there and I'm going straight over to the right 2 units. And so if you can just try to use the same distance like from here to here and just go this off of this direction, so maybe about here, And then if I do the same thing going to the left about here, and then if you want to go in other directions, you certainly can, like here and here, and you can do the same on the bottom. And then when you're done, you want to connect those points to make a circle. And when you're finished with that, it should look a little bit something like this. In the next lesson, we'll kind of start to talk about, well, how can I recognize this without having to go through the process of completing the square and doing the algebra. But for now, I think that it's really a good idea for us to do that. I like the book's suggestion of, for each of these, is transform them to polar equations. If you need to do that first, I think that's a great idea. You may not need to do that on some of the easier ones like we started with, like r equals 4. But even if you don't have to, I'd still like you to. I think that's good practice for us. And then you might find that some of the ones, perhaps like r sine theta equals 3, and this one here, r equals 4 sine theta, I think you'll find that it's actually quite helpful to do that so that you can know what your graph looks like. So I have one more example, but I can see my video is getting pretty long here, so I'm actually going to skip this one. And I'm going to go ahead and share the homework with you. And that homework is on page 600. And I'd like you to do 16 through 30 evens, and then 31 through 38 all. Now the 16 through 30 evens, those are just like the examples we've just done. Those ones, they ask you to convert to a rectangular equation and then to graph. And again, I would really like it if you could try to use that polar grid. Again, if you could print that off at home, that would be ideal. If not, see again if you could try to copy and paste a graph into some sort of utility, either on your Chromebook or your phone, that you can plot some points and play around with. You know, worst case scenario, you could try to draw them by hand, but again, that's probably not going to be very fun. And so if there's any way you can use those, maybe find an app or even a website or something that can help you draw them, I think that would be to your advantage, and we really need to have that practice. I do want to discuss this problem. There's one question in the homework that you kind of need to know this one about. Most of the homework you can get by without having to do this problem, but there is one problem like this in your homework, and it's actually a matching problem. So the 16 to 30, going back to that, that's just like what we did in our notes, and then 31 to 38 will be matching. I think if you've done this first, the matching will actually be quite easy, and you should be able to get through that very quickly. But one of the matching problems is like this one. So if at the very minimum you just want to get that question right, it'll be the one that's left over. And when you're done doing all the matching, there'll be one that you're like, I haven't really done this one yet, I'm not quite sure. And it's going to be the one that's like this one. And the reason I'm kind of saving it, I'm going to go ahead and stop my video, is because we're going to talk more in depth about an example like this in the next lesson. But what I'm going to do is I'm going to stop my video, and if you're really anxious and you're curious and you want to go ahead and get a head start on that, I'm going to make a bonus video that just does this problem. And if you, again, you don't really need it to get through the homework. It'll just be the one that's left over on your multiple choice. But if you want to go ahead and look at it, it'll kind of give you a heads up on what we're going to talk about in the next lesson, and could reinforce those topics at that time. All right, so thanks for listening. If you want to check out that bonus video, I'll post it in the Google Classroom alongside this one. As always, reach out if you have any questions. Let me know how I can help. Thanks for listening.